I wanted to start off today talking about scientific method. You know, eventually science has worked so well because eventually things like scientific fraud are discovered. Sometimes it takes time. And so, for example, there are stories where people hide data. You know, if the data isn't supporting what their conclusion is. There's a very famous case of a person hiding data. Happened in Japan, and this person worked in the laboratory of a Nobel laureate, and there was some data that didn't quite. And this happens a lot in science. When you're doing science, sometimes the data just is confusing, or it's hard to interpret, or it doesn't support, your hypothesis that you proposed. And so eventually it was discovered that this person was hiding or manipulating some of the data, and at least for that person, they went to the extreme of committing suicide because of that. Let me show you this person here. This didn't happen. This was not that long ago. I don't want this here. But she had falsified some data or hid some data, and it turned into a huge scandal. And it was too much, I guess, for her to bear, and she ended up taking her own life. And so, eventually that type of stuff, when you think about it, eventually somebody's going to find out, especially if it's important research, because the scientists are always trying to repeat the stuff and do this kind of stuff. And so, but this isn't the only case. I mean, this is tragic. This was in 2014, and when I heard this, I thought, my God, Anyway, then there's this other case here. This wasn't even the principal research. In 1987, my father, a scientist at the U.S. National Institute of Health, killed himself after a member of his lab committed scientific fraud, and he got caught up in the investigation. And that's pretty intense as well. And so eventually, things catch up. And apparently, I just heard this story, what was it, yesterday or this morning, that the CDC was hiding data because the data didn't quite support or could be misinterpreted or whatever. But we never hide data. In science, you don't hide data. You give all the data out. But the CDC, being an organization, obviously they aren't going to go to extremes like this, and probably nobody's going to take responsibility for something like that. But it just goes to show you, eventually things will be found out. And this is how the science. You can't hide things forever, basically. That's it. And so when I was going to, graduate school, different professors had different philosophies about cheating. Some professors, they didn't care. Go ahead and cheat. You know why? Because eventually you're going to be found out. It depends on how far you go along. But, it might take time. But it's going to catch up at some time. You'll have an oral exam, or you'll have something where, you can't hide it. You can't hide that. And so this is kind of the tragedy here, but it's one of the successes of the scientific method. The CDC, even this big organization, obviously they can't hide it forever, that they were hiding data. hiding data. Why? Because, and this happens, like I said, it doesn't quite support, what we're saying. So, what we were talking about earlier. We're looking at the exercises here, so we'll go through some of these quickly and take a look at how we name. So we were looking at 1A complex ion having chromium-3 as essential ion and 2 ammonias and 4 chlorides as ligands. So when we write the formula and name these, we follow the different sets of rules. Did we already talk about this one? Yeah? Okay. So when we write the formulas, the essential metal comes first, and then the ligands. And what comes first, the anion ligands or the neutral ligands? Anion ligands, so the chlorides. And we end up with how many chlorides? 4 chlorides and 2 ammonias. Okay. However, when we name this, what did we do with the name? Alphabetical. And, here's not a big deal, I think, because there have been so many different nomenclature systems introduced that if we don't follow the rules, nobody's going to pounce on us, for doing that. But we said we're going to name these alphabetically according to the name or the symbol in the formula. According to the name. That's going to alleviate some problems. And when we name these, a lot of people put the name of the metal first. We like to call this chromium, tetrachloride, diammonia or whatever. But we don't do that. For the complexes, we flip it and do the ligands first, right? And then we'll do it alphabetically. So amine comes before chloro. And so we said this is going to be diamine. Is that 1 M or 2 M's? 2 M's. Diamine, tetrachloro, tetra for 4. Chloro is chloride, we change the ending. And then this is going to be chromium or chromate. Chromium or chromate. Well, it depends on the overall charge. When we look at the charge, the chromium they're telling us is 3+, chloride is -1, so +3 minus 4 is -1. Ammonias are neutral, so this is getting a negative here. So chromium or chromate? Chromate. And what's the charge on chromate? 3. Roman numeral 3. So this is what we have. Diamine, tetrachloro, chromium. What do I do? This is going to be chromate. Roman numeral 3. Purposes behind these names? What the purpose is behind these names, so that when people want to order something, they can find it in the catalog. more easily, or when people talk with each other. When they talk with each other, they'd like to use the same naming system. So if you're using one naming system and the other person's using another naming system, then there could be potential for confusion. Why not use the chemical formula? Some people have proposed that. So some people have proposed this. You call this chromium, tetrachlorine, dinitrogen, hexahydrogen, something like that. Some people have proposed that for naming. The nomenclature system, none of them are perfect. This is why people are still debating this thing. Like, say, for example, this. Do you know magnetite? Geologists will know magnetite because it's a mineral, it's magnetic. This is iron and oxygen. How would you name that? Well, we could name it magnetite, but following our rules, Chem 1A rules for nomenclature, how would you name that? That's not Chem 1A rules for nomenclature. Chem 1A rules for nomenclature is when you have an ionic compound, we name the ion. So you name the cation first and then anion. People will know what you're talking about. This is why one of the proposals is to skip all that and then just call this tri-iron tetraoxygen, or tri-iron tetraoxide, or tri-iron tetroxide. Get rid of the A. But this one fails our nomenclature system because what's the charge on iron? Yeah, what's the charge on iron? We have two common iron ions, there's iron 2 and iron 3. What is the charge on this one? Well, normally in Chem 1A I do this. Okay, so we have 3 irons. This is the way I do nomenclature, and we have 4 oxygens. Oxygen goes first at 2 minus. So that gives us -8. And so this has got to be +8. And we have 3. So each one of these must be +8 thirds. +8 thirds. +8 thirds. 8 thirds would be 2 and 2 thirds. And so this is iron. We call this iron 2 and 2 thirds. 2 and 2 thirds oxide. Does that sound right to you? No. And so this is the failure of the nomenclature system, one of the failures. There are many other failures. And the failures are primarily because of this. This is not iron 2 and 2 thirds. What is this? What this is it's 1 iron 2 plus and 2 iron 3 pluses. So 3, 6, 8. And so this is what we call mixed cation salt. And so, but even though there's this failure of the nomenclature system, this is, as best as we have. This is why, growing up, I grew up with lots of Roberts in my neighborhood and friends. And so everybody had a different, if you called everybody Robert, you don't know, which Robert are you talking about? Robert 1, 2, whatever. And so we all had variations of the name, Rob, Robert, Bob, Bobby, all these variations so that we knew who we were talking about. And the same thing, if you have a lot of variations of the same name, then things can get confusing. On Wikipedia, you can look and see a lot of these variations. Want this one. sometimes on Wikipedia they'll give you all the variations of the names. Usually we look on the CRC Handbook of Chemistry and Physics and whatever else, and we can see the variations. This they name iron 2, 3 oxide. Iron 2, 3 oxide. Well, that's okay too. And so people have different names, but the basic question is why have a systematic nomenclature name, and one of the reasons is so we don't get mixed up in what we're talking about. All right, the next one is a nickel 2 with cyanides. This one, do you know what the coordination number of this one is? Well, these are all monodentate ligands. So this is what we call an octahedral complex. And its coordination number is going to be 6. It's going to have 6 ligands on there. And so we just draw a chromium in the center, and then we'll have 6 bonds to it in an octahedral configuration like this. And then we put the chlorines there. There's choices for the chlorines, like we can put them next to each other or we can put them opposite. If we put them opposite, that's called the trans. If we put them next to each other, that's called cis. But we're going to talk about trans and cis later. We're going to skip it right now, but there are what we call 2 isomers for this, a chlorine opposite and a chlorine adjacent. I'll just draw one of these. This would be the more symmetric trans isomer. Here. Okay, B is a complex of iron 3 having coordination number 6 and cyanides as ligands. So we throw in the iron 3, that was a chromium 3 there, and then we could put the 6 cyanides here. Cyanides are carbon donors, and carbon donors are excellent. Ligands are excellent Lewis bases. In fact, this is a very stable. Even though it contains cyanide is very poisonous. It's quite stable and fairly unreactive. Now, each cyanide is -1, and so that means the whole thing is going to carry what charge? Yeah, 3-. And then again, we name the ligands first. So this would be hexacyano. Iron or ferrate? Ferrate. The charge on iron is +3, so we add that on there. Sometimes, I'll write the word ion. The word ion is not really necessary because if you know the nomenclature system and you know the formula, you can figure out that if it's an ion or neutral. And so we don't really need the word ion there. For complexes. For something like sodium, we do need the word ion because sodium is the same name whether we're talking about Na or Na+. And so it makes a huge difference. And so here we are required to write ion in there, otherwise we think we're talking about sodium metal. And so sodium ion is required here, but for here, it makes no difference. All right, that's a coordination number of 6. How do you know if it's a coordination number of 6 or a coordination number of 4? You don't. We just look it up, in the table and see. They're going to tell us. Or here, they tell us. In this case, nickel. Nickel 2. And in fact, nickel 2 likes a coordination number of 4, and it likes to form square planar. How do I know that? Well, there's no theoretical analysis there. How I knew that nickel likes a coordination number of 4 and square planar structure is because that's what I learned. That's what scientists observed. And then what's the the hypothesis or what's the theory underlying that? And that theory that's underlying that is something called crystal field theory. Crystal field theory we're going to talk about later, and it has to do with the bonding and that kind of stuff. There. And so we don't know, if it's coordination number 4, it's either tetrahedral or square planar. You can't use VSEPR. Earlier we could use VSEPR, valence shell electron pair repulsion, to determine if it's going to be tetrahedral or square planar. That's pretty easy to do. But here, no. And so the tetracyano complex of nickel, this is nickel 2+, is going to carry a net -2 charge like this. And if we write the formula out for this, it'll be NiCN 4 2-. Everything in the brackets is complex. This will be tetracyano nickel or nickelate. Nickel or nickelate? Nickelate. And so this is tetracyano nickelate. And the positive charge on nickel is 2, so Roman numeral 2. Now we could pair this with regular anions and cations. And so how many potassiums would I need to balance out the charge here? And so these are ions. The ions like to form ionic compounds. And so here would be an example of ionic compounds with hexacyanoferrate. We could take iron 3+. If we take an iron 3+ and then a hexacyanoferrate 3-, then we can form the ionic compound FeCN6. And now how would I name that? Well, we have a set of rules for naming this, and the set of rules would be name the cation. Well, the name of the cation is pretty simple. It's just iron, Roman numeral 3. Ion, or just iron 3. And so the name of this compound would be iron 3, the name of the cation, and then the name of the anion. The name of the anion is hexacyanoferrate 3. And so to name this whole thing, we'd call it iron 3 hexacyanoferrate 3. That would be the name of that compound. Here we just need like a +1, or we could have +2. If we had a +2, we could do something like this, magnesium 2+. And so what we could do is we could take the magnesium 2+, and then we'll need 2 of those. And so we can make this compound, Mg, okay, square bracket, CrCl4, NH3, 2. We need 2 of these complex anions to balance out this cation. And so what would I call this compound? Well, the name of this is it magnesium Roman numeral 2? No, this is just the magnesium ion, right, because it's fixed charge. And so this would be called magnesium, the name of the cation, and the name of the anion would be diamine tetrachlorochromate 3. And so I'd call this magnesium diamine tetrachlorochromate 3 compound. Okay, what are the coordination numbers? Now the coordination numbers we can figure out based on the ligands, how many ligands we have. But sometimes people get mixed up because of bidentate ligands and hexadentate ligands. Sometimes there's one hexadentate ligand, so they think the coordination number is 1. But it's hexadentate, so the coordination number is actually 6. And so that's where some confusion comes up. So what are the coordination number and the oxidation state of the central metal in each of the following complexes? Name each complex. So I'm going to go through these quickly, and then you go back through and do them for your homework. Did I give you the homework? No, not yet. I need to give you the homework this one. Okay, so how would we name this? hexaamine cobalt or cobaltate? Cobalt because it's a positive. Positive and neutral, you just use the normal name. Negative, we use the 8. So it would have been cobaltate if this were a negative. So this is hexamine cobalt 2, Roman numeral 2. All one word, hexamine cobalt 2, or Roman numeral 2. Parentheses. And don't forget the parentheses. Next, coordination number. 6. If it has a coordination number 6, it's octahedral. Well, this is an octahedral complex. Okay, how about this next one, B? Hexafluoro. Now, fluoro, is fluoro spelled F-L-O or F-L-U? F-L-O-U. F-L-O-U would be like flower. Yeah. F-L-U-O. F-L-U-O. This is oftentimes when people do this, I see it, flower. Hexaflower. Fluoro. But it's hexafluoro. Aluminum or aluminate? Aluminate because of the negative charge here. So this is called the hexafluoroaluminate ion. What's the coordination number?
I have a question.
Uh-huh.
Why is the fluoride first? Why is it first even though
Yeah, that's because you have to flip it. You're right. Why is it first? I don't know. Somebody decided that, and that person had the authority to say. There's a governing body called IUPAC. Have you ever heard of IUPAC? IUPAC, International Union of Applied and whatever Chemistry. They decide the nomenclature rules. Not everybody accepts them, you know. Some people will go against the grain and go their own way. You know, some people, there's common names, you know. There's a big dispute about common names, you know. Yeah. But IUPAC is trying to standardize this so that people know. I'll tell you, these are not overtly complex. Some of these, you got these gigantic molecules. You got a gigantic molecule. How the heck are you going to name that thing? It's so complicated. Let's say you have like a biological molecule. It's got 100 atoms in there. You know, how are you going to name that? It's crazy. And so the names, if you want a systematic name where somebody can figure out, oh, that's what you're talking about. Most of the times, people just call it a common name. Well, that's, you know, named after me, or named after this scientist, or named after that. You know, but what people want, they want a systematic system that they can figure out, what the heck are you talking about? You know, you go to these conferences. I go to scientific conferences. You go to a scientific conference and you go, what the heck is that person talking about? You don't know what they're talking about. Normally, and that's normal because they're talking in their own, you know, pidgin language or jargon or whatever. You know, people who are in that group will know what they're talking about because they're using that. And so when I listen to talks, sometimes I just try to write down as much as possible, and later on I'll go figure out what they were talking about. You know. Aluminum or aluminate? Aluminate. And the charge on aluminum? +3. And coordination number? 6. Structure? Octahedral. Okay, let's go on to this one. How would you name this one? Tetracyano. Copper or cuprate? Cuprate. Charge on copper? 2. So hexacyano copper, or not copper, hexacyano cuprate 2. And so I'll tell you, even though, you know, I tell you it's flipped, you know, you got to remember it's flipped. Formula, metal first, name, ligands first. People always write the metal first. When I give a nomenclature quiz on this thing, this stuff, people will consistently, there are going to be a group of people who are going to call this copper first, copper tetracyano something. And then there's going to be people who are going to call this copper 2 cyanide or copper 4 cyanide. I see so many variations of the name. I see like some of the, if I see like 5 different variations, are all 5 of those acceptable? I guess, maybe people can figure out what you're talking about, but do you want to always have to be thinking in terms of 5 different names for the same thing? I mean, 5 different names for Robert, okay, yeah, I'll deal with that, But 5 different names for everybody is too much. Too much. So this is why people are, again, and this is why you might think it's unfair. Why am I being marked off for that? And necessarily, it's because of the, try to keep consistent with the rules up to a point. The rules, like I said, are not laws. Let's go on with this one. How would we name this? Yeah, now this just happened to work out here. Do you do the bromo first or the amine first? And why? It's not because of the order here. It's strictly alphabetical. So even if the amine were written over here and the bromo were written over here, it'd still be, tetraamine because amine comes first. A. We're doing it based on the name. A for amine rather than N or H for the symbol or the formula. And so tetraamine dibromo, chromium or chromate? Chromium, what's the charge on chromium? Well, amines are neutral. Bromine, that's bromide, which is -1, which means chromium must be +3. +3 minus 2 gives us +1. What's the coordination number of this? Coordination number is not 4, 6. Coordination number is 6. Excuse me, bromo is monodentate, amines are monodentate. And so it would be something like this, where we have the amines here, and then there's 2 bromos stuck on there. The coordination number 6 is the octahedral. Let's name this. Now, you can use abbreviations only in the formula for 3 things. Oxalate, ethylene diamine, which is EN, and EDTA, ethylene diamine tetraacetato. Otherwise, we're not allowed to use abbreviations like this, and we're not allowed to use abbreviations in the name. In the name, we have to spell it all out. And so how would you name this? Yeah, trioxalato. Now, oxalate ion, what's the charge on oxalate? -2 times 3 is -6. -6 plus what gives us -4? It's got to be +2. And so that would be cobalt or cobaltate? Cobaltate. So this is a trioxalato cobaltate 2 ion. What's the coordination number of this? It has 3 ligands, but each of those ligands is a bidentate versus monodentate. And so the coordination number is actually 6. We're allowed certain abbreviations after, you do the shortcuts after you learn the long way. And so after we learn how to draw the oxalate in there, the long way, we'll do the shortcut way. The shortcut way is like this. And we write OX here, so we don't have to write the whole thing. So this is one oxalating ligand. This is a second oxalate ligand here. And this is a third. Each oxalate ligand is bidentate. And so this is actually coordination number 6. Okay, then we go on to this one. S2O3 2- isn't that common, but it is a common reducing agent. You know. Do you know the name of this? Thiosulfate. It's when you take sulfate. We'll do sulfate with the way it's normally written, the expanded octet here. Again, there's some debate about whether it expands the octet or whether it's an octet rule or an octet law. There's some debate about that. But this is the most common. Oh, what was there a question? Oh, because I'm showing this is sulfate. When you have thio, do you know what thio means? Thio means replace an oxygen with sulfur. So we have alcohols. Alcohols are OH. You know what thiols are? Thiols. Thiols are SH. So you take the oxygen and replace it with a sulfur. So if we take sulfate like this and make it thiosulfate, then all we do is remove an oxygen and replace it with a sulfur, like that. And so that's S2O3 2-. You might think it's an ite because of the 3, and you're right, it would be an ite, but it's still an 8 because we just removed one of the oxygens, but replace that position with a sulfur. Sulfate is not a reducing agent. You know, sulfate's already maxed out. The sulfur is +6, the oxygens are -2, everything's maxed out. Thiosulfate is a reducing agent. Thiosulfate is a reducing agent not because of this sulfur. This sulfur is +6. It's because of this sulfur here. This is 1, 2, 3, 4, 5, 6. So this sulfur is 0. Sulfur is kind of a big atom, and so thiosulfate is a very common reducing agent that we see. What would you expect? Thiosulfate, monodentate, bidentate, tridentate, tetradentate. What would you expect for thiosulfate? There's a problem with it being bidentate. Which 2 oxygens would you pick, maybe? Well, this is tetrahedral, so all these oxygens are 109, so it doesn't matter which 2 you pick, they're all adjacent to one another. If I draw it flattened out like this, square planar, it's not square planar, it's tetrahedral. And so if we pick these 2 oxygens here, which are 109, like this, and have the metal here, we can bind to it. That would be bidentate. But what would the problem be if we did this bidentate? So we can just do the structure here. If we try thiosulfate as a bidentate, so I know it's tetrahedral, I'm going to pick these 2 oxygens here at 109. Actually, all the oxygens are equivalent. You know, all the oxygens are equivalent. They're 4 resonance forms. Actually, 3 resonance. Well, whatever. It depends on what I do with the sulfur. I could say if I make it, if I follow the octet, then there are 4 resonance forms. If I don't follow the octet and do this expanded octet, then there are 3 resonance forms. I'll just do the expanded octet here because that's the most common way it's written. So let's have these 2 oxygens do the bidentate, you know, the claw, chelate, onto the metal. What's the problem with that, if any? What's the metal here? The metal here is silver.
Ring.
Yeah, ring strain. If we have this bind like that, we're going to get a 4-membered ring, which is going to be strained. So thiosulfate is not a bidentate ligand, it's a monodentate ligand. And so, well, that's our analysis of thiosulfate. It's going to be monodentate, but anyway, let's go on with this. How would we name this? Okay, is it going to be di or is it going to be bis? It's going to be di thiosulfato, dithiosulfato, silver or argentate? Yeah, it's going to be dithiosulfato argentate. And what's the charge on silver? Well, thiosulfate is a -2. So that's 2 times -2 is -4. -4 plus 1 gives us, it's got to be +1. So we're going to need Roman numeral 1. However, you know, maybe this is the reason why people screw up like this. AgCl. What do we call AgCl? Do we call that silver 1 chloride or just silver chloride? We call it just silver chloride because there's only one charge on silver. It's +1. And so you might ask, why the heck am I writing Roman numeral 1? Because there's only one charge on silver and it's +1. Yeah, you have a point there. It's not really necessary. But to be consistent with the rules, we don't want too many exceptions, you know? Write the Roman numeral, unless you have silver. But then you might have cadmium. Cadmium's always plus. Cadmium's always plus. Well, silver here is, cadmium's always +2. So write the Roman numeral unless you have silver and cadmium. Or zinc. Zinc is always +2. Or et cetera, et cetera. So, you know, rather than having too many exceptions, we'll just go ahead. Even though it seems unnecessary to write the Roman numeral, we're going to go ahead and write it. Otherwise, it's too many exceptions will pop up and it's going to be a headache. So what's the coordination number of this? 2. Coordination number is 2. When we have a coordination number of 2, the structure is easy. What is the structure? Linear. When we look at the structure, we're not looking, you know, sulfate or thiosulfate tetrahedral. We're looking just at, you know, around the metal. You know, when I look at this structure, it's kind of complicated, but when I look at chromium, it's just octahedral. You know, the bonds to chromium. I just look at the bonds to silver. It's linear. All right, let's name these ones here. Yeah, okay, diamine. What about this chloro? Do we do diamine A and then monochloro? Diamine monochloro? No. Does this chlorine belong in the complex? No. This chlorine's outside the complex, so we're not going to name that. Let's name the complex first, which would be diamine, silver or argentate? Silver, and the silver Roman numeral 1.
Can you go over again how you decide between silver and
It depends on the charge of this. We know the charge on chloride is -1, so the charge on this whole thing must be +1. This is an ionic compound. An ionic compound where we have a normal run-of-the-mill anion, which is chloride, very common anion, but the cation is kind of weird. And so this is a complex cation. Since it's a cation, we just use silver. If it's an anion, we use 8. So here, let's just look. Is this going to be a cation complex or an anion complex? Cation. Sulfate is a normal run-of-the-mill anion, which is -2. Okay, now this one, is it a cation complex or an anion complex? Uh-huh.
So I thought that we said that silver in the dithiosulfate was +1, and we called it argentate.
The dithiasulfoto?
Yeah.
Yeah. Silver is +1, but the whole complex is not. We're looking at the net charge of the complex. So each thiosulfate's a -2. And so that's -2, -4 for 2 of them. And it's not the charge on the silver. When we write the Roman numeral, here, let's do that. -4. The silver here is +1. You know, each thiosulfate is -2, -2. And so what we're looking at is not the charge on the silver, which is positive. We're looking at the overall charge. The overall charge is going to be, well, +1 -4 gives us -3. And so we're looking at the net charge on this. And so this is why, if this is negative, it's the 8. This one is a trick one because this one's neutral. There's no charge on it. And so this is neither an anion or cation. So what we call that is we call it a complex compound, or complex, you know, in this case, molecule. This is a very famous one. Actually, one of the structures of that is very famous. But let's go ahead and name this first. What is the name of this? Dichloro. And then what was it? Ethylene diamine. Dichloroethylene diamine. Platinum. And what's the charge on platinum? Not -2, +2. Yeah. And so this is called dichloroethylene diamine. Platinum, Roman numeral 2. So if it's neutral, we just use the normal metal name. We wouldn't call it platinate. It's only if it has a net negative charge we call it platinate. What's the coordination number? This. Some people will say 3, but 3 is wrong. What is it? 4. The coordination number is 4. Then the next question we have, is it going to be tetrahedral or square planar? So we look it up and we see that it's square planar. Platinum 2 complexes like to be square planar. So, just from observations, empirical observations, that's what we see. When we look at the d electrons and the bonding and that kind of stuff, then this is what we call a D8 complex. It has 8 d electrons, and D8 complexes like to be square planar because it results in the lowest energy. If we do a square planar structure versus a tetrahedral structure.
Just clarifying for A, would that just be diamine, silver, chloride?
Oh yeah, this would be diamine, silver 1. We have to write, the diamine, silver 1 is all one word. And so for A, I would write it like this: diamine with 2 M's, silver, Roman numeral 1. That's the name of the cation. And then we just have the normal anion, which would be chloride. We don't have to say monochloride, because in ionic compounds, we can figure out how many chlorides we need to balance out the charge. So if this cation is +1, then we only need 1 chloride. And so we don't use the prefixes here. And so this wouldn't be, over here, this wouldn't be called monosulfate, it's just sulfate. Here, this would not be called disodium. This would just be called sodium because we know the anine's got a -1 charge, or -2. Actually, anion would have to be -2 here because we have 2 sodium. Here's a bit of nomenclature for you. Most people don't use this name. Most people will use the name here. We have 2 isomers. Do you know what isomers are? Isomers, when you draw Lewis structures, you always think about isomers because when you draw a Lewis structure, you might be able to draw more than one Lewis structure for a particular formula. And so what isomers are is they have the same formula but different Lewis structures. And so we have 2 structures for this. It's square planar. So we have this. This results in cisplatin and transplatin. Cisplatinum has this structure. It's PT. And we put the 2 chloros adjacent to one another, like this. And then the ethylene diamine. Ethylene diamine's what is that, monodentate, bidentate? Bidentate. Remember, it was like the NH2, CH2, CH2, NH2. The lone pair is going to be used to make the bond. Or what people do is they'll just write a curved line here and write EN. And so a lot of people abbreviate this PT. Some people don't even write the N's here. They'll just write EN. And so this is a lot of people don't bother with the lone pairs either. They figure, everybody knows how many lone pairs there should be on there. But since I see that not everybody does, I just write it there. Because we want to keep track of the lone pairs. This one, cisplatin, is a very famous chemotherapy agent. Chemotherapy is like for cancer treatment. They have certain chemicals that can kill cancer cells. This is one of them. Cisplatin. The discovery of this is very interesting. The discovery of this was there are some researchers at the University of Michigan, and they had a I don't know, petri dish or something of cancer cells, and so they wanted to see what effect electric fields have on it, electric and magnetic fields. So they put in 2 electrodes. The electrodes happened to be made out of platinum. So they put the 2 platinums in this petri dish of cancer cells and then turned up the voltage. And what that generates is it generates a voltage. The voltage is called electrical potential, which generates electric fields. Like one of the platinums becomes positive and the other platinum becomes negative. Well, one of the chemical properties of platinum, do you know one of the chemical properties of platinum? Redox. One of the redox properties of platinum is it's what we call a Nobel metal. Nobel metals are coinage metals and certain other metals. And those metals are very resistant to oxidation, like gold. It's very hard to oxidize. In other words, platinum is an awful reducing agent. It's awfully hard to take electrons from platinum. So one of the weird things that happened was when they put this into this medium, the platinum electrodes started to react. And that's very weird because that's the reason they chose platinum in the first place is because they didn't want it to react. The platinum shouldn't react chemically. Platinum should just generate the electric field. But the platinum was reacting. And whatever the platinum was making killed all the cancer cells. And so so this brings up one of the challenges in chemistry. One of the challenges in chemistry is what the heck was it making? What are the products of that? And the problem is they generated too little to analyze. You know, sometimes you get these very complicated mixtures. You get a very complicated mixture. The first step is you have to separate the mixture. You separate the mixture using physical means. The physical means would be like filtration, chromatography, distillation, you know, all the standard physical separation techniques. But you get something like that and you start doing the physical separation techniques, and by the end, you've lost it all, because each separation you lose a little bit. You lose a little bit, lose a little bit, and then you have nothing left. So they didn't take that approach. There are other sophisticated methods where they can use spectroscopy and other things, but those things, when you got a complicated mixture, it's very hard to do. And so you know what they did? They got a chemical catalog and looked at every single platinum compound that was available and bought all of them. They bought all the platinum compounds that were available and then started testing each one of those individually, and then they found this one. This was it. This was it, because what happens is the shape of this square planar, so it can get stuck in the groove of the DNA or whatever, and it can't replicate. Those cancer cells can't do anything. You know? But chemotherapy, well, this can damage healthy cells too. You know, so there's a cost to this, but if you can concentrate it, I guess, in the cancerous cells, then it's better. So anyway, this is cis and trans platinum, or if we use a systematic name, that. Okay, then we go on to this one. What would this one be? Penta aqua, bromo, chromium. Chromium 3. Yeah, this is good. Penta aqua bromo chromium 3. Cation. This one? Well, first let's try to figure out the name of the complex, and then we'll name the whole thing. The complex, coordination number of this is 6. Yeah. All these are monodentate ligands. This one would be called what? Just the complex. Or we could name the whole compound. The name of the cation's just a standard cation. Rubidium +1. Rubidium is alkali metal. So this would be rubidium. Now the name of the anion is complex. It's complex anion. And so we call the anion tetrafluoro silver or argentate. Argentate. Tetrafluoro argentate. This is weird. Tetrafluoro, that would be, okay, rubidium's +1. And so that means silver must be, this whole thing must be -1. So -4 + 3 gives us -1. But didn't I just tell you that silver only has one charge? And what charge is that? +1. So something's wrong with this one. This one throws up a flag. Something weird about this. And so you can look it up. If silver +3, So yeah, there's definitely something wrong with it. Silver 3 fluoride is unstable bright red dimated compound containing silver in the unusual +3 oxidation state. And so this would be similar to like gold 3. However, gold 3 is the more common oxidation state of gold is +3. But normally what we do is we do this. Silver +1. This silver 3, we can make things in unusual oxidation states. But you know, those are just kind of, you wouldn't be doing anything with this because silver 3 would be you would expect to be a powerful oxidizer in this particular state. Like for example, in the reason I was using the reason I was using fluorine at UCLA was I was trying to make iron in a very weird oxidation state. I was trying to make this compound because there was a group that claimed to have made an iron 4 compound. So what are the common charges of iron? 2 and 3. So there's a group that had claimed that they made an iron 4 compound. And so I just wanted to repeat that experiment to see if I could generate the iron 4 compound. And it was to get it in that unusual oxidation state, you need a very powerful oxidizer. The powerful oxidizer I was using was liquid fluorine. Fluorine's normally a gas. So I liquefied the fluorine. Not only did I liquefy, if you liquefy the fluorine, the temperature is super cold. I liquefied it using liquid nitrogen, which is very cold. And then I sealed it and I removed the liquid nitrogen, and then I heated it up. I heated it up to very high temperatures, and so I had a high pressure, high temperature mix of fluorine and then reacted with iron to try to get iron 4, this compound. I thought I had made it. You know, the reaction went okay, but the problem is I'm working in the glove box, and I could not break my reaction vessel free. My reaction vessel is made out of a very resistant metal called Monel. It's like stainless steel. And I had this little cap on there. So I was trying to break the cap free. So I had wrenches inside there. And I wasn't able to break it free inside the glove box. Now I regret it. I should have. I think back at this. I spent a lot of time on that reaction. I should have brought a hammer inside the glove box and tried to hammer it there. Instead, what I did was I took it out of the glove box, took it downstairs. There's a machine shop in the basement of UCLA. Took it to the machine shop, put it in the vise, and then started to hammer away at it. When I hammered away at it, then, you know, it broke free too much. I just wanted to loosen it, but not break the seal and then bring it back upstairs. It broke free. It broke too much. I looked in there. It was green for an instant, and then poof, it decomposed. And apparently this iron 4 was green. And then I ran out of time because I left UCLA at that time. But I really wanted to do that one again because I thought I had it. But that happens, you know. You don't stay there. So silver 3 is very unusual. Silver 3 compounds, no. Silver 1, yes. You know, it's unusual, very unstable. But you know, somebody made it, and I guess somebody repeated making it.
Do they use it for anything, or do they just make it?
A lot of these things are used as precursors for other things. So you have something very reactive, like for example, sodium metal. Do they use it for things? Yeah. You know, sodium metal, the stuff that they dumped in Lake Lemoore, I use that all the time. In fact, I used to buy like a kilogram of sodium metal. And the kilogram of sodium metal comes wrapped in foil, this metallic packaging, and it's sealed in a container that's pressurized with nitrogen. And so,
Also covered in oil or something?
no, the stuff I bought wasn't covered in oil, but you can buy stuff that's covered in oil. The stuff that's covered in oil are people who work outside in normal air. The stuff I bought, because I didn't want to have to clean the oil off, you know, because it's a hassle. So the stuff I bought had no oil. It was just surrounded with nitrogen, but you have to open it in the glove box. If you open it outside in air, it's going to start to oxidize right away. So I use that to make some unusual things, some pretty reactive things, like some very powerful base. Like, how do you make the powerful bases? The bottom. There are different ways to do that, and so one of the bases I used to use a lot was sodium methoxide, which is a pretty powerful base for reactions. And so we use these things to make things with all the time, very reactive chemicals. So you can make some unusual stuff. And you want to make unusual stuff and check their properties to see if there's some useful properties for those, or at least to see if you can understand, theoretically, certain things, theoretically what to expect and this kind of stuff. So people make this kind of stuff. AgF3 bright red, AgF, ASF6 deep blue, AG3F8 deep red, and then see what kinds of properties we get for this. So, in other words, this should have thrown a flag, because in Chem 1A you learned that silver only has one charge, +1. This is silver +3. Okay, so let's go on to this one. What's this? Disodium or sodium? Sodium. Pentacyano. Okay, now this one, what do we call NO? Well, you'll see nitrosyl quite a lot. Nitrosyl, but the nomenclature people got together and changed that again. So let's look at a common nitrosyl. So this is off Wikipedia. So nitrosyl's NO, or nitric oxide, or nitrogen monoxide. NO, you might think, what's the use? Metal complexes of NO. It turns out that in biology, biologists are really into metal complexes quite heavily because there's so many that occur in the body. But NO, nitric oxide, won Molecule of the Year. Did you know that?
You did not know they had.
You didn't know they have Molecule of the Year? Oh, where have you been?
I don't know. Under a rock, clearly.
At home for the last, 2 years?
I don't think I would have figured it out if I left. You're doing better than that.
1992. Molecule of the Year. Oh, you were born yet. Okay, all right, that's good. All right, yeah, well, I remember when NO won Molecule of the Year. So, 1992. Because normally when you think of NO, you think of NOx. When you have a car, you got to bring it to smog check. And at smog check, they don't want too many NOx, like NO, NO2, and 2O4. They don't want... NOx are oxides of nitrogen because NOx are poisonous, and they cause smog. And so we don't want... And so most of the time when people think of NO, they think of smog, photochemical smog, poison. But it turns out that NO is an important biological messenger that regulates a lot of blood processes. In fact, There's one treatment for COVID that people were looking at, and that was inhaling NO. You know, you think inhale NO, that's toxic. You know, they're inhaling NO, or you know, to try to. Anyway, nitric oxide. If you want to read about it. Who warrants this molecular year? Yeah, I know. Molecular year is kind of weird, but who warrants it? Science Magazine. Science Magazine is one of the premier science journals in the U.S. And so if you have a publication in science, it's really well respected. And so they go through the whole story here about NO. And, you know, I don't really follow either. I don't even know who won Molecule of the Year last year, because I haven't been paying as much attention as I probably should. They're molecules of what? No. 2021. 2020 vaccine, COVID.
It's the breakthrough.
Oh, breakthrough of the year. Molecule of the year.
They stopped.
maybe everybody lost interest in molecule of the year.
They're like,
I can't imagine they ran out of molecule. That's odd.
No wonder I never heard of it.
Yeah, okay.
I'm sure that's the reason.
Let's say 2021. Maybe everybody lost interest, but they're still doing it.
Oh, but it's not science.
Oh, it's not science. Well, I guess Science Magazine lost interest in it.
They decided to do like
CNE News is another big one. Let's take a look. CNE News is CNE News is a weekly news magazine for chemists and chemical engineers. CNE News posted all the COVID-related science articles for free. This is a publication that's published by the American Chemical Society. And the American Chemical Society has a whole bunch of journals of their own. So what was the molecule of the year? Oh, wow. They did a poll for the molecule of the year. This is pretty interesting. So what won the poll? Porous ionic liquid won the poll for 2020. Well, this is interesting. In its +6 oxidation state, this aromatic 12 porphyrin nanoring produces a ring current that induces magnetic fields. Oh, pretty interesting. Porphyrins are these ring structures that are aromatic. They have these alternating double bonds, and all the p orbitals line up. Nature is the other big magazine. Nature. This is the porous ionic liquid. It has cavities that are approximately 6.2 angstroms wide, big enough to capture alcohols and CFCs, chlorofluorocarbons. Previous porous liquids couldn't grab anything larger than methane or carbon dioxide. researchers at the University of Cambridge made the new liquid. So maybe they're trying to use this liquid to capture CFCs, chlorofluorocarbons. You know, photochemical smog. You know, the generation of NOs. We have the ozone layer there that protects us. When these CFCs get exposed to ultraviolet radiation, they make free radicals. Anyway, let's just finish these quickly and then we'll move on or take a break. All right, so let's name, are we on these now? F? Okay, what's this? Sodium, and then, now the question was, what do we call NO? Should we call it nitrosyl, which was the traditional name, or should we call it the new name, nitrogen oxide? Which was, I think, the name that we're supposed to use. Does anybody recall? And so that was the monodentate ligand. Let's take a look at the ligands here. And then we'll look at, there's a table of monodentate ligands here. Oh, actually, sorry, not nitrogen oxide, it's oxido nitrogen is the new name. So, oxido nitrogen.
Is it gonna have two O's then?
Yeah, let's take a look at that. Let's go back to that one here. Try to figure out if they're going. Now, sometimes we eliminate double vowels. Sometimes we leave them, like tetraamine. We have AA. We leave it AA. Sometimes we eliminate, like, carbon monoxide or carbon monoxide. Well, carbon monoxide, we eliminate that. And so it depends on how it reads. So this one would be penta cyano, because cyano, well, now, then we have the pentacyano oxido, was it? Pentacyano oxido, nitrogen. Ferrate, charge. Three. Uh-huh.
I know it sounds weird, but would it be oxido nitrogen?
Oh, oxido. The O we only do for anion ligands. So if we have a neutral ligand, no. And so let me go back to that chart which will show you. If you look at the chart, no, none of the neutral ligands will have the O ending. And normally they have just the normal name. So for example, the name for C5H5N is pyridine. So the name of the ligand is just pyridine. And so there are only a few that get special names. CH3NH2 gets a special name here, methanamine. NOCONH3. These are the special name ones. Anything else just gets its normal name. So all the means will get its normal name usually. Now going here, yeah, we don't add the ON. It's just oxidonitrogen. So we'll just leave it as oxidonitrogen. Now the question is, do we call it pentacyano? Or should we call it pentacyano-oxido? Or should we call it pentacyanoxido? Noxido or pentacyano-oxido? Yeah. So this one, cyanoxide, might get confused, I guess. So probably we'll just leave it at that. Cyano-oxido, etc. But, I don't know why they changed it to such an awkward name, oxidonitrogen. That's just weird. And I don't think most chemists would, after you've been calling it nitrosyl for 30 years, it's hard to switch to such an awkward name. And so I don't even know if Wikipedia's updated their page. They haven't.
Is it also more if it's being used as a ligand versus
Yeah, only if it's used as ligand.
when it's oxide?
Right. If it's not, then we just call it its normal name, nitric oxide or nitrogen monoxide or whatever. All right, let's just quickly finish the rest and then we can move on to the next step. I myself am not going to memorize that. The ones you really should memorize are aqua and amine. Those are the ones. Those are the two most common ones, aqua and amine. Carbonyl, carbonyl is important because it's carbon monoxide. And carbon monoxide is very poisonous because we have lots of different ligands. Even oxygen, O2 can be normally when we think of O2, it's not a base. But if we think of O2, this is the normal Lewis structure for O2 that we draw. This can be an electron pair donor. It's not the best, because there's no negative charge. Both of these are neutral. But if we have iron 2, this is very important because iron 2 in blood, and this will make a 6-coordinate octahedral complex. And the important thing is this one binds and then breaks off easily. But if there's a competition between carbon monoxide and oxygen, carbon monoxide is going to win. And so they're both fighting for the same acid. Well, O2 is pretty poor. CO is great. In fact, carbon donors are the strongest. And so we're going to get carbon monoxide poisoning. So carbonyl is kind of an important one for biology. And so carbonyl, you might want to know. Oxidonitrogen is also, I don't know, the nomenclature should be consistent. They should call this oxidocarbon. If they won't be consistent.
Do you want oxidonitrogen or do you want
I want nitrosyl, but that's my opinion, you know. And I think I don't know. Somebody else wanted the other one. But anyway, we'll get back to this. I'm not going to be a stickler for it. I don't really care what you use. If you want to use oxidonitrogen, fine. If you want to use nitrosyl, fine. I don't really care. But, you know, I just don't want to get involved in that. And so I'll tell you right now, I'm not going to ask you that one.
Great.
Thank you. Appreciate that.
Yeah. All right. Write appropriate formulas for the following. So potassium hexacyanide. Oops. Okay. This is another thing that changed.
So this is a new book?
Yeah.
Do you know what version of the book?
Well, do you have the older version? I don't know.
What is the older version?
The white cover you have there? That's a new version.
The new?
Yeah.
Okay, here.
You know what? Petrucci's been around for decades. You know what chem book I used when I was taking Chem 181B? Petrucci. I used Petrucci. Petrucci passed away years ago, but the book still lives on. It's a good book. I used Petrucci, and but my version of the book versus today's version of the book are completely, night and day. Today's version of the book is much more sophisticated. What's that?
The dedication says, we the authors dedicate this edition to Ralph H. Petrucci, who passed away, and the final edits of this edition will be complete.
Okay. That's it. Yeah. Yeah. All right, take a look. Do you see cyano? This is a chemical company. And this is their catalog, online catalog. I can order this stuff. And so they apparently they haven't been made aware of the nomenclature rule change. So if I wanted to order some of this, potassium hexacyano, this is cobaltate. Was that ferrate? I don't remember. But this is a common chemical. No, this is ferrate, but this is the same thing. Okay, so the new name for cyano was cyanido, but it doesn't matter, cyano, cyanido, I don't really care. Nor does, I think, anybody else really care. But this would be, potassium ion is just K+. Hexacyano, though, ferrate, we've seen before. And so, this is FeCN6 with a 3- charge. How many potassiums will we need to balance out the charge? 3. So the formula for this is going to be K3 FeCN6. And that's what we'd call potassium hexacyanoferrate 3. Bis ethylene diamine copper 2 ion. Cu En2 charge. Yeah. Coordination number? 4. Tetrahedral or tetrahedral or what was the other one? Square planar? Yeah, this one happens to be square planar. Next one. Penta aqua. Here they did the double vowel. Penta aqua hydroxido aluminum 3 chloride. So let's do the first one, penta-aqua hydroxido aluminum. So what gets written first? Al. Okay, then what goes next? Okay. Yeah, it's going to be hydroxido. Why? It's an anion. Now, do we need parentheses? Sometimes yes, sometimes no. So let's leave off the parentheses. If we can leave it off and it still makes sense, we'll leave it off. If we leave it off and it doesn't make sense, then we'll put them on. Like, what's next? H2O5. So here I leave off the parentheses. Does it make sense? No. And so I need the parentheses for sure for this. But now, if I put parentheses around the H2O, do I really need parentheses around the hydroxido? No. Hydrogen can't be a Lewis base, unless it's hydride. Okay, what's the charge on this? +2, so that means I'm going to need how many chlorides? 2. Okay, so that would be that. The D. Amine chlorido bis ethylene diamine chromium 3 sulfate. So what do I write first? Cr. And then what comes next? Well, amine you'd like to, but we have to do the chloride first because it's anion. So CrCl, and then amine or ethylene diamine next? Amine next. Both amine and ethylene diamine are neutral. And so how many amines do we have? Just one. And then comes ethylene diamine. And we have how many of those? 2. And so here we got to think about parentheses here. So where should we put the parentheses? Probably around the amine, we need a parentheses around that.
Yeah.
And then if we have 2 ethylene diamines, we'll need a parentheses around that. And so we end up with this. Okay, what's the charge on that? Do we need around if there's only one? Yes and no. The problem is there could be ligands like this. Like say I had an NH2 with a Cl on there. And so this is kind of like an amine, although it's not that great because the chlorine's on there. And so I don't want it to get mixed up that chlorine is bonded to the N or, as a ligand or separate. And it's not neither of these, so I put the parentheses around the ammonia here so it just doesn't get mixed up in that case. Yeah, this is going to be +2, so we'll just need 1. Chromium is +3, chlorine's -1, this is 0, this is 0. So +2, whole thing. And sulfate's -2, so this balances out as a +2 -2. Tris ethylene diamine iron 3. Tris means what? Which one? Oh, the second part of this? I know it's not because the iron 3. Iron 3 is the end of the name, end of the thing. And so this has got to be 2 separate ones. Yeah, so we'll just do the first one and then the second one and then figure it out from there. And so the first one is the trisethylene diamine iron 3 is going to be Fe parentheses En 3. Charge on this one? Yeah, 3+. Okay, let's do the second one. Fe parentheses Cn 6. Charge? minus 4. All right, so how many of these will I need, and how many of these will I need? Yeah, I could just do 4 and 3, just cross multiply that. And so this is going to be FeCN 3, 4, FeCN 6, 3. So then I'll have plus 12 and minus 12, which will be 0. Okay, so this is where we have a complex cation and a complex anion. So it's a bit weird here, but we'll have both. All right, let's take a break now, and then and the other stuff. We're going to move on to chapter 15. Chapter 15 deals with equilibrium, but really, I'm going to call this Chem 1B stoichiometry. You know, you have Chem 1A stoichiometry. We do stoichiometry a little bit different in Chem 1B because we do more types of. In Chem 1A, you know, there's either a reaction or no reaction. If there's a reaction, then we just do our standard stoichiometry. In Chem 1B, we're going to look at those partial reactions. You know, do you remember the partial reactions? Like, the partial reaction would be like acetic acid. Acetic acid is a weak acid. It partially ionizes. We have different words for it. It partially ionizes, partially hydrolyzes, or partially dissociates. And so the Chem 1B, let's just take a look at acetic acid right now, which is just CH3COOH. And so partial ionization, partial dissociation, we have CH3COO minus plus H plus. It's a weak acid. And so if it's a weak acid, we just expect it to weakly ionize or weakly dissociate. And so weak acid equals weak electrolyte. And so we have weak ionization, dissociation. Dissociation, it just dissociates into ions. Ionization is dissociates into ions. That's it. Another way we can look at this is we can look at it in terms of an acid-base reaction, hydrolysis. In fact, in Chem 1B, we're going to look at most of these. So this is equivalent to this. Is H plus very stable in water? Not at all. And why is that again? H plus is not stable because of it's awfully high. Well, it's an acid, but it's not very stable because of its high. Even if acetic acid were a strong acid, H plus is still not stable because of its high.
No, you want, we don't know.
Well, it's not charged because it's just plus 1. It's charged. Well, what did you say? Density?
Yeah.
It's very dense, but we would say charge density, right? Because of a very high charge density. And so in reality, when we see this equation, this is the shorthand way of writing it. In Chem 1A, I like to use H plus. I don't like to hassle with H3O plus. And so when I do chemical reactions in Chem 1A, I always use H plus, you know. But technically that's not as accurate as using H3O plus. H3O plus is when H plus reacts with water, and we just do that in one step here. So acetic acid plus H2O liquid. This gives us CH3COO minus acetate and H3O plus. And so weak acids are weak electrolytes. They weakly ionize, they weakly dissociate, and they weakly hydrolyze. And so weakly hydrolyzed. Hydrolyze just means, you know, react with water. Hydrolyze just literally means breaking water. You know, So let's do some stoichiometry here. If I did some stoichiometry, let's say I had 1 mole of acetic acid, and I had excess water. So my limiting reagent is acetic acid. So I have 1 mole of acetic acid, plenty of water, and I have, let's say I'm starting off with 0 moles and 0 moles here. If you did the stoichiometry, you do, this is a limiting reagent, excess reagent problem. What's your theoretical yield of hydronium? Well, yeah, it was a 1 mole. You get 1 mole of hydronium because for every mole of hydronium, we need a mole of acetic acids. So normally in Chem 1A stoichiometry, we just did, okay, I got 1 mole of acetic acid, and then I use the mole ratio. The mole ratio here is 1 mole of hydronium forms for every 1 mole of acetic acid that reacts. And then that means I'm going to get a theoretical yield of 1 mole of hydronium. Okay. Does that look familiar? But there's a big problem. Am I really going to get 1 mole of hydronium? That's assuming what? It all reacts. But does it all react? No, it only partially reacts, so I'm not going to get 1 mole. If I don't get 1 mole, well, how much am I going to get? Well, in Chem 1A, you say you get a little bit. But in Chem 1B, a little bit is too vague. You know, it's too qualitative. We need to be more quantitative in Chem 1B. And so what I want to do is I want to calculate how much are we going to get of hydronium. Now, partial reactions, you know, this is the problem. In Chem 1A, you never did stoichiometry on partial reactions. We just avoided it entirely. In Chem 1B, now we want to include stoichiometry of partial reactions because there are a lot of them. And so when do we see partial reactions? It depends on the driving force, you know, the driving force. So let's take a look at acetic acid. What else does acetic acid react with? Well, acetic acid reacts with any base that's stronger than what? Than acetate. But, you know, there are bases that are a little bit stronger, and there are bases that are a lot stronger. You know, so for example, if I have a base that's a lot stronger, which I ran out of room here because of the position here, but let's go with a base that's quite a bit stronger. Like hydroxide is tremendously stronger than acetate. And so if I have acetic acid reacting with hydroxide, which is a very strong base, then what I'm going to produce is this. I'm going to produce the conjugate acid of hydroxide's water. So I'm going to produce water. And so when I compare the strength here, acetic acid versus water, acetic acid is a much stronger acid, and water is a much weaker acid. And so what we're doing is we're going very downhill in terms of energy. Now we have to flip our world upside down when we look at bases. If we flip ourselves upside down, then the strongest base is at the bottom. And so going downhill here, this is a much stronger base, hydroxide, than the base that we produce. The base that's going to be a product here will be acetate. And this is a much weaker base. And so what we see is this as a tremendous downhill process in terms of enthalpy, in terms of energy. And so there are 2 ways that, actually, I should have left that up there, but it's all right. So I'm going to take my acetic acid, which is CH3C. See, they did CO2H, which is fine. It makes it more compact. But I'll just do COOH here. CH3COH plus, let's go with hydroxide. Like that. The base, any hydroxide, AQ. And this is going to produce acetate and water. So this could be sodium hydroxide. If it was sodium hydroxide, it would look like a double replacement reaction. which is fine. You could use sodium hydroxide there. So what we're seeing is we're going from a stronger acid, acetic acid, to a weaker acid, which is water, and a stronger base, which is hydroxide, to a weaker base. This is what we call driving force. The driving force dF for the reaction. And this has to do with energetics. So here, in terms of an energy level diagram, we put energy here. Then combination of acetic acid and hydroxide is a higher energy combination than acetate and water. And so this kind of just rolls downhill here. You're on a bicycle, this would be easy to go downhill here. And the farther we drop, the more favorable it is. The situation is, it would be hard to roll uphill. Because when you look at chemical reactions occur when there are collisions. And so if I have an acetic acid molecule colliding with a hydroxide ion, I'm going to get a reaction and it's going to roll downhill. But on the other hand, this is an acid, water, and this is a base, acetate. And so what if an acetate and the water come together? There could be a reaction too. If an acetate and water come together, what am I going to form? Well, I'm going to form acetic acid and hydroxide. And that would be like going uphill. But is it going to be so easy to go uphill here? No, because that's a pretty high energy barrier to climb. Maybe some might be able to do it. It depends on how energetic they are. Not every acetate and not every water has the exact same energy. In fact, you should know at room temperature, is every acetate moving at the exact same energy, exact same speed as every other acetate? They're just like robot clones? No, they aren't. In fact, like if you have a cup of water, the cup of water is at 25 degrees C. Let's say 25 degrees C is like room temperature. And we think about the water molecules. If you try to visualize the water molecules in a cup of water, here, is every single water molecule behaving exactly the same as every other? No. What we see is a distribution of energies. Some of the water molecules are going to be so energetic they can actually vaporize off the surface. And that's called evaporation, or vaporization. But most of them aren't. We don't get that much water vapor off the top because it's just a very small fraction of water molecules that can vaporize. And that energy distribution is called what? So if we look at it, all the molecules are energetic enough to roll downhill. This is easy, right? But going back up the hill is going to be tough because maybe only a very small fraction of those can. And so what we see something like this. This curve looks like a bell-shaped curve, but it has a high energy tail. Have you seen that curve before? Where did you see that curve before? Yeah, energy. This is this on the y-axis is population. On the x-axis is energy. You saw it as kinetic energy or speed. This is called the Maxwell-Boltzmann distribution, or thermal distribution, or kinetic energy distribution. And what it says is that if we're at 25 degrees C, not everybody has the same energy. And if I'm looking at a sample of 25 degrees C water, most of the water molecules will have this energy around here. A small fraction will have kind of low energy, and a small fraction will have kind of high energy. There's a cutoff. This small fraction, some of these will have enough energy to escape the liquid. And so there's going to be a cutoff here. Like, let's say above this energy, all these water molecules can escape the hydrogen bonding and London dispersion forces holding them in liquid. So, in Chem 1A, we just say, okay, we're going to assume 100% reaction. But, when we do that, we're ignoring that very small population that can actually make it back up the hill. And that very small fraction is negligible. It's going to be very small because this is a gigantic hill decline. And so the bigger the hill decline, the smaller the fraction. And so if we're looking at a giant hill in the reverse direction, that fraction is going to be smaller because the amount of energy it needs is quite a bit more. And so in Chem 1A, that fraction is kind of negligible. It's too small to worry about because let's say the hill is so high, it costs this much energy to climb back up. And so that means the population is very thin. You have a minuscule population. And in fact, for this reaction, we would just say that, there's such a minuscule population, we're going to ignore any reverse reaction taking place. And so, no reverse reaction here. And so in Chem 1A, the stoichiometry is kind of easy. We just say it's a one-way reaction. It's a one-way reaction. If I start off with 1 mole of acetic acid and excess hydroxide, how many moles of acetate will I have? Which is 1 mole, and that's fine. Now, what if we had something like this, though? Hydroxide is a strong base, much stronger than acetate. But what if we tried to react it with bicarbonate as the base? Here. So rather than reacting it with hydroxide, we'll take bicarbonate and then try this reaction. And so acetic acid plus bicarbonate, is that a long, steep downhill? No, it's just kind of right there. And so what's that going to form? Well, what that's going to form is it's going to form carbonic acid. Carbonic acid is just a little bit weaker than acetic acid. And then we're going to form acetate. Well, acetate in this case is just a little bit weaker than bicarbonate. So the driving force is totally different here because it's not such a steep hill. Everybody's going to make it down the hill. But once we're down here, there's going to be a population that can make it back up the hill here. And so in this case, if we're looking at this here, so we have acetic acid, and now we're going to react it with bicarbonate. So what forms? Okay, this is our base here. This is our acid. So acid loses a hydrogen. So we're going to form carbonic acid. Carbonic acid is unstable. That goes to H2O and CO2 liquid, or CO2 gas, sorry, no, H2O liquid and CO2 gas. And acetate. That's what we're going to get here. But the cutoff is like this, this is at 25 degrees C, so let's do this at 25 degrees. The hill's not so steep. So the hill barrier, to climb back up is like this. So there's a more significant population of molecules that can react in the reverse direction. And so in this case, we're going to have both forward reaction. Forward's preferred because it's downhill. But the reverse is not preferred because that's uphill. But since it's not so steep uphill, and the population is like this, then there's going to be a significant population that can go backwards. Now, when we have a case like this, what's going to happen, you can't stop the collisions. You can't say, okay, you and you stop, because they're just going to collide. It's just random. And if we're going to have these collisions random and we have this population that looks like this, then we're going to have reverse reaction occur no matter what. And so now if we have 1 mole of acetic acid, how many moles carbonic acid, or how many moles of acetate do I form? You don't know, because we need to know what population makes it back up the hill. And you think, well, you know, what's happening is, this is called a dynamic equilibrium, and you can't stop it. There's going to be downhill and uphill occurring, back and forth. And so the population that makes it back uphill will fall back down. But as soon as those fall back down, some more will react and go back up. And so pretty soon we'll hit something called a steady state. And that steady state is what we call an equilibrium, where things just don't change. You've had this react, and and then it's done. It's done, but it's not done. It's done reacting, but it's not done reacting completely. It's never going to react completely. And so what we end up with is this. Even though this is stronger acid, stronger base going to weaker acid, weaker base, there's a big difference in the driving force between this. This is a much weaker driving force than the others. And so the stoichiometry is all of a sudden complicated, because now this reverse is significant in this case. So that reverse is significant. Okay, let's look at another example here. The next example is, let's say if I take acetic acid and react that with an extremely weak base like nitrate, is anything going to happen? No, nothing's going to happen. If I take acetic acid and react it with something weak, that's too steep of a climb. You know, there might be a very tiny fraction that might be able to make something happen, but it's negligible, right? Because it's too steep of a climb. But what if we had acetic acid reacting with nitrite? Well, you think, no, we're going uphill. But how far uphill is that? And even though we're going uphill, it's favored downhill. Even though it's uphill, is there going to be a certain fraction of the population that can make it up that hill? This is, if you have a group of bicyclists, you know, if you have a group of bicyclists and the hill's not so big, then yeah, a large fraction can make it up. Maybe not everybody, but a large fraction can make it up. And so this is not so steep. And so even though we're going from this is a weaker base here than acetate, what we're going to form is nitrous acid. Now, nitrous acid is a weaker acid. And so that's telling us we're going uphill. Going from a stronger acid to weaker acids uphill. But how steep of a hill is that? It's not that steep. And so what we see is that, okay, it's uphill, so the majority of the population isn't going to make it, but you know, for the forward reaction, we might have something like this, or something even bigger, a bigger percent of the population. And so we're going from stronger acid to weaker acid, and then we're going from weaker base to stronger base. This would be a weaker base to stronger base. So that's not favorable, so this whole thing's going uphill. And so when I look at the reactions, it's looking like this. It's like CH3COOH plus nitrite here, and then we're going to go uphill a little bit to CH3COO minus and HNO2, nitrous acid. And so here we're going from a weaker acid, more stable, and a weaker base, more stable, to a stronger base, less stable, and a stronger acid, less stable. Obviously, this is favored in the reverse direction, but a tiny percentage of the population can make it up that hill. And so in Chem 1A, when we didn't have a driving force, we just said no reaction. Well, no reaction to stoichiometry is easy. Nothing changes. But in Chem 1B, we have partial reaction here. And this partial reaction means that we can still get it. So in Chem 1B, we're looking at these scenarios where, you know, it's not so steep uphill or it's not so long of a trip downhill. And so we can see significant reactions in both directions. And so this is what we're going to see. Some of these are going to make it up. If they make it up, then they're going to come back down. But as these come back down, new ones will come back up. And we set up this circle. The circle is the dynamic part. We have constant up and down reaction. So we're in this circle. But once we hit this state, you know, because it's only a certain population, we'll hit the state where the forward reaction, right, that is the number that are making it up, exactly equal the number that are making down. And so this is the equilibrium part.
So you said since it's going uphill, is acetic acid considered a stronger acid over nitrous acid?
No,
It's still
it's still, normally we say no reaction. If we're going from weaker to stronger, it should be no reaction. But that's not taking into account that, you know, there's a small population that are so energetic that they're going to react.
But if the uphill driving force is more steep, then it will be no reaction.
Then it would be no reaction, right? And so in Chem 1A and also in Chem 1B, when I do these, this is no reaction, we predict. You know, we're going uphill, no reaction. It's unfavorable. Energetically, it's unfavorable. But now what we're looking at is we're looking at the small nuance. You know, how unfavorable is it? Because we got to take into account the population. If the population were all the same, then it would be easy. No reaction, nobody's going to make it up that hill. But unfortunately, not everybody's exactly the same. We have this small population here of high energy that can make it up unfavorable, the unfavorable direction. And so,
Is there also like a set like driving, like uphill driving force where there is the difference between partial and no reaction? Like,
yeah, there is. But it's not completely set in stone. It depends on how concerned you are with minute quantities of reaction. So let me give you one example. One example is, normally we don't really consider this one. H2O liquid plus H2O liquid. H2O liquid plus H2O liquid, we have bronzite acid-base reaction occur there to form H3O plus OH minus. Now this is very weak, very strong, very strong. So this is a huge uphill climb. And so if we're at H2O liquid, which would be way down here in terms of energy, and then hydronium and hydroxide, powerful acids and powerful bases, this is way up here in energy. So this is a huge climb. And so normally we think, no reaction. No reaction. And so, so if I had 1 billion water molecules, how many out of that billion would react in this case? So if my population were 1 billion, you know, and the top is way up here for this because it's such a steep climb. You know how many would react? 4. 4 out of 1 billion. Is it? If we only have 4 out of 1 billion, would you worry about that much? No, I mean 4 out of 1 billion is too small, too insignificant to worry about. Unless you are measuring the pH of water. If you measure the pH of water, do you know what the pH is? The pH measures how much hydronium there is in water. And the pH of this water is pH 7. Well, actually it's not pH 7, but it's supposed to be pH 7. And what that means is 4 out of 1 billion comes out to 10 to the minus 7 molar. 10 to the minus 7 molar is 1/10 of a micromolar. 1/10 of a micromolar is nothing, you know? So insignificant. But it depends on how minute you want to get into this. If you're doing Chem 1A stoichiometry, are you really going to calculate how many grams of hydronium are formed and how many grams of hydroxide? No, because it'd be so tiny. In Chem 1B, we're going to look at all reactions, even explosive reactions like this. Explosive reaction would be like hydrogen plus oxygen. Hydrogen plus oxygen is going to yield water. How many waters are going to go back uphill? You know, and so I have my water here. It's already downhill. So let's say I formed this water from taking hydrogen gas and oxygen gas, having this huge explosion. I got the water as a product. How many of those water molecules are going to go back uphill to form hydrogen gas and oxygen gas. Like, you'd say like nothing. I mean, do you worry about the hydrogen decomposing into hydrogen and oxygen? No, because there's this huge climb uphill, right? But in Chem 1B, we're actually going to calculate how many would. So if I had, whatever, we're going to go ahead and calculate it. It seems like ridiculous. In Chem 1A, we'd never do that. But in Chem 1B, we're going to treat all reactions as potentially reversible. There could be things preventing it, but in this case, the number is going to be so tiny, it's what we call negligible when we have that. Negligible, in fact, we can just ignore it. Nobody's going to be worrying about this. If you did, then this would be a great way of producing hydrogen. You just let the water sit there and you can collect the hydrogen gas and the oxygen gas, And so we'll treat all reactions kind of the same. The hill might be huge and it might be minuscule. And then later on we'll say, well, it's so insignificant. The reverse reaction of this is so insignificant, it's just one way. That kind of thing. So how do we figure out what the population is that can make it up the hill in this reaction? How do we, well, if we knew, the size of the hill, then we can, and we knew this kind of, thermal distribution here, then we can kind of figure it out, using thermodynamics. We can figure this out, thermodynamics, this energy, right? We're going to do that later when we get into thermodynamics. Initially, we aren't going to calculate how much makes it up the hill here. You know how we're going to figure it out, how much makes it up the hill? We're just going to measure it. These are just going to be entirely empirical. That is, what we're going to do is, we're kind of curious how much makes it up. So what we'll do is we'll take some measurements. We'll let this react and then figure out at the end how much acetates produced, how much nitrous acid is produced, how much acetic acid we have left over, and how much nitrite we have left over. And we just do some chemical analysis to figure it out what that ratio is. And so how we do Chem 1B stoichiometry is we have to have some knowledge. It's not a percentage though. For example, if it were always a simple percentage, like let's say 1% of the molecules can make it up the hill, then it would be easy. Chem 1B stoichiometry would be easy because we could just say 1% reaction, 99% no reaction. Then it would be easy. Well, the problem is that if you change the concentrations, let's say I increase the concentrations of both or decrease the concentrations of both. If I increase the concentrations of both, then the percentage actually goes down. And if I decrease the concentration of both, the percentages actually go up. It's kind of weird. Or if I increase one and decrease the other, then it changes the percentages that react. So I'd love to be able to use the percent, but I can't use the percent because the percent changes depending on what my initial starting concentrations are or amounts are. And so what we do is we just do this totally empirically at first. And so let's take a look at this. Reaction here. We're going to look at this redox reaction. We're taking two copper 2s and a tin 2. We're going to react them. Copper 2 is an oxidizer, tin 2 is either oxidizer or reducer. In this case, it's going to be reducer. So the tin 2 is going to lose electrons, copper 2 gains, and we end up with copper 1 and copper tin 4. The redox reaction. So let's look at this experiment. These are concentrations, molar concentrations. So we start off with 0.100 molar copper 2 and 0.100 molar tin 2. Well, we see that copper 2 would be the limiting reagent because we need 2 coppers for every tin. And so normally in Chem 1A, okay, the limiting reagent, we react that completely. And then we're going to have some excess tin left over. So they mix this together. And they give it enough time to completely react. And so after it's done reacting, there's no more change. And so once it's done reacting, we hit a state of what's called equilibrium. Equilibrium just means there's no more change. Did all of the limiting reagent react? No. You know, how much of the limiting reagent reacted? Well, this is the nice thing about starting with 0.100. We call that 100% initial. We lost 36%. How much, what percentage of that reacted? 64%. So we had 64% of our limiting reagent react. Can you guys see that? Because we have 36% left over. And nothing more is going to happen. It doesn't change beyond this. So how did I know 64% reaction? Well, how I knew it was 64% reaction is because they measured it. It's this entirely empirical. So they measured it, they got 64% reaction. Okay, that's great. So I know this undergoes 64% reaction. So let's try another set of data here. So now we're going to go uphill. That must be the downhill direction there. But was it steeply downhill? If it was steeply downhill, it would be 100%. Because that means 34% didn't, or made it back up. Okay, now we're just going to start with products here and let it go uphill. If it goes uphill, then I predict only 34% will make it back up the hill, and 64% will stay down the bottom of the hill. Isn't that what you'd predict? So going backwards, we predict 34% reaction. And so let's take a look. Going backwards, which one's the limiting reagent? Well, we need more copper. So going backwards, copper will be the limiting reagent. And so this is the limiting reagent, this is the excess reagent. So I predict 34% of the limiting reagent will make it back up the hill. Does that make sense? So let's take a look. Well, how much made it back up the hill? So if we start off with 100, we're left with 43.3. And out of that 100, 56.7 made it back. So we actually have 56.7% make it back up the hill. You see that? And 43.3% stay down. So that's weird, right? Well, let's try one more. Now I don't know which way is uphill and downhill because it looks like, you know, going this way more made it down the hill, and then going backwards it looks like more made it. So maybe it's downhill this way, but not downhill as much. You know, it's kind of weird. So in this last experiment, let's just start with 0.100 of all of them. So if we start off with 0.100 with all of them, then no, this is kind of even. We're going to start with a group of bicyclists up here and a group of bicyclists here, and then see which way it goes. And so now can you tell which way is the downhill direction? Well, it looks to me that the downhill direction is, well, we start off with 0.100 and then we lost some going this way. This was the limiting reagent, right? And so how much did we lose? Well, we started off with 100, we ended up with 92.2, which means we lost 7.8%. So 7.8%, well, where did that go? Well, that went into products. So you see here it's 7.8% higher. So this is the downhill direction, but what was the percent reaction? 7.8%, 54.7%, 60 whatever percent. So how can we do stoichiometry when we're getting all these random amounts of reaction? How can you do stoichiometry? In other words, I want to predict. So let's say I go with new ones. I go 0.200, 0.200, 0.200, 0.200. Can you predict? When you do 0.200, 0.200, you would think, okay, that's similar to this. So we should get the same, 7.8%. But you know what? You don't get 7.8%. Now you get a new number. And so at this point, you might just say, okay, forget it. You know, Chem 1B stoichiometry is too complicated. We don't want to deal with it. And so here's our data. In science, what do? You collect your observations, and then what do? You look for patterns and trends. And so the next step is, do you see any pattern and trend? So one quick way of looking for patterns and trends is by graphing it. You know, if we can graph the data, then maybe we can see what's going on. And so let's go ahead and graph this data. Okay. Here's a graph of the data. What they did was they start off with initial. And so in this case, the blue, they started off with initial 0.100. The blue is tin 2. And then this magenta, they started off with 0.100, which is the copper 2. And then they started off with no product. And then they just monitored the concentrations as they changed over time. So the reaction started. As the reaction starts, the reactants are being consumed. As the reactants are being consumed, the product is being formed. And eventually, the reaction stops. It doesn't really stop. Eventually, things stop changing at the macroscopic level. And at the macroscopic level, you can see the concentrations have stabilized here, and you're at the end. This is what we call the equilibrium. So in this gray box, this equilibrium has been reached. There's no further change. And so look at the pattern. I look at the pattern, blue, black, magenta, green. And so that looks like the pattern there, right, for reaction. Then I go over here, and in this case, I start off with just products, no reactants. Do I see the same pattern, blue, black, magenta, green? No. Then I go over here and I look for the pattern, and does this pattern match any of the other two patterns? No. And so here I'm looking for a pattern, but I don't see the pattern. Graphically, I don't see any pattern there. And so sometimes it's not the graph. Sometimes we don't see the pattern, or you might stare at this. Maybe there is a pattern there, you just don't recognize the pattern. And so that's it. Maybe there's a pattern there, we just don't recognize it. So then you start looking at it maybe mathematically. Maybe there's a mathematical pattern in there. And so we look for a mathematical pattern next. This is the old one, but the first mathematical pattern we look at is the percent. Well, that failed. There was no pattern to that. The next mathematical pattern is maybe there's a ratio. You know, at equilibrium, that is, once this is done, we'll take a ratio. Maybe the ratio of the products over the reactants. So they took the ratio of the products over the reactants for all the equilibrium, and there was no pattern there. And then maybe the stoichiometry had something to do with it. And so maybe what they did was they tried this pattern. They took a ratio of products to reactants, except doubled this number, because we have 2 coppers, so maybe they tried doubling this. If they doubled this and then multiplied it by that and divided by those, is there a pattern there? No, there was no pattern there. No pattern. And so they tried a whole bunch of different patterns, mathematical patterns, until they found one. They found a pattern that worked. Do you know what that pattern is? Take a look. Rather than doubling, like say here, this number here, actually this is not the one we want. We're looking at the equilibrium. There's no pattern in the initials. At the equilibrium, let's look at the pattern. So what they did was they took the copper 0.064 and squared it. So there's a 2 there. Why squared? They were just trying everything, you know, because they're starting to give up on finding the pattern. So they just tried squaring it. So they squared that, and then the tin they just left as is, and then this copper they squared it, so 0.036 squared, and this tin over here they just left alone. And then they calculated this, and it came out to 1.49. Okay, then they look at experiment 2 and repeated the same thing. So with experiment 2, they did the same thing. They squared the coppers and left those, and then took the ratio, and they got 1.48. 1.4, that's very close, you know. It's close within, let's say, round off. And then they did experiment 3 and did the same mathematical expression and got 1.48. Do you see a consistent pattern there? And so in all three of these cases, the ratio came out the same, or roughly the same. And so that means that if we know the ratio, which is going to be about 1.48, we'll just take the average because we don't know which one's right. Maybe the 1.49 is right, 1.48s are slightly off, or one. So the best thing is if we have three of them, we're just going to average the three, which is going to come out to 1.48. And so what we do is we have this pattern. Now what we want to do is we want to make sure this is consistent. You know, is this a fluke or is this a law? You know, if it's a law, then this pattern holds for everything. But if it's a fluke, there's a rule. You know, this rule worked for this case, but it didn't work for other cases. And so in this sense, then, we test it. And so you go 0.200, 0.200, 0.200, 0.200, and you know what? The ratio at the end comes out to 1.48. So no matter what they put in initial, it could have been anything. At the end, they still got 1.48. And so what we call that is a law. And they test it, you know, the different reactions will have a different number here. And so we're going to have a law, and the law is this. And this has been tested with lots of different reactions. A law, the best way to write a law is mathematically. If we can write some simple mathematical formula to define the law, that's best. And the simple mathematical formula to define this law is if we had a reaction, A is the coefficient, little a, big A is the reactant, dot, dot, dot. This is going to give us G plus HH plus dot, dot, dot. Then the pattern's this, and we're going to call it the equilibrium law, or the equilibrium constant. This is called the equilibrium constant. And in this case, I'll put a little C here because we'll have a little designation. The concentration of G at equilibrium, that is when the reaction is done, raised to the little g power, H raised to the little h power at equilibrium, divided by A little a at equilibrium, B little b at equilibrium, is equal to a constant. So if we always get the same ratio at equilibrium, then this gives us a way to figure out the stoichiometry. Anyway, I'm going to stop here. Then we're going to do the check-in next. Okay, thanks.
Just down the hall. That's okay.
It's like a statue. That's what I do. Yeah, we give this the window. Okay. Yes.
Okay, see you next week.
It's like a weird way to do it.
Because for none of these, that's like really dirty.
You have an ID card?
Is that on the outside? That could be on the, or is that on the inside?
Seems on the inside.
Yeah. Just bring them to the stock room and ask them.
And I have one plastic one. That's okay, or
Keep the plastic ones.
Okay.
Plastic ones are more handy to have than those.
Okay.
I have one that's like 10
Yeah, the plastic ones aren't on the inventory sheet. Those plastic ones are what they call disposable pipettes. Save them because they come in handy. The droppers are the glass ones with the black bulbs on them.
At least he's a brown bear, right?
He's a black bear.
Oh, it's a black bear. Okay. That's a very large black bear, but not a grizzly bear. So,
Yeah.
oh yeah. No.
He's a big boy.
If I see a grizzly, I'm like, goodbye. Yeah, I don't think I'd ever be somewhere out here. There's like wild polar bears.
Polar bear?
Yeah, but I don't think that like where we would go is like a tourist. You're gonna have polar bears and shit. Maybe if you're hiking, you might have grizzlies, but I don't plan on doing Arctic hiking. Yes, but if you want to Alaska, you can.
What?
You learn to fire a rifle and then you just shoot it.
You don't want to shoot a polar bear.
Well, whatever people do, they have to do something. What else are you gonna do? Fight?
Yeah.
Like that.
Frank darts? No, I think you shoot
They
it.
have the right to bear arms. That's what they
Maybe
really
you
did.
need an Uzi, but you probably should.
You thought they were doing like arms.
Hey, thanks. See you.
They have the right to literal bear arms.
Bye.
There's a little boy taking that. It's him with arms and literally bear.
Thanks. See ya.